What's it mean to be a root of a polynomial? Kind of touched on this, but not specifically. A root is the same thing as a zero, or same thing, crosses the x-axis. So roots, the root of a polynomial is the same thing as the zero of a polynomial, where it crosses the x-axis. What is that x value where it crosses the x-axis? What about the term rational? What's rational mean in a math context? What I want you to think of rational for this is rational is going to be some sort of a fraction. Okay, so like 3/4, 1/3. That's what we're thinking about rational. Okay, we can write it as a fraction. Okay, so that rational, that simply means a fraction. So the rational root theorem, now we're going to have zeros that are fractional amounts. Like our zero could be at 1/3, or it could be at -2/7. So that's where we're getting rational roots. And there's a certain step process that we're going to follow to be able to determine those rational roots. Okay, not on your handout yet. But first thing we're going to talk about is what actually makes up the rational root theorem. So we know for any polynomial, there's limited number of possible roots. Okay, it's where it's crossing the x-axis, so there's not an infinite number. So if we had, say, an x² function, we actually could use the back up. Let's use like the quadratic formula in the discriminant piece under the radical. That tells us how many solutions there'll be. With a quadratic, a degree 2, we know there's either 0, meaning it's not going to cross, but it's just a U shape maybe already above the x-axis, or a U shape already below the x-axis that's going down. So we could have 0, we could have 1, where it actually touches the x-axis, and we could have 2. And that's specific for quadratics, because that would be a degree 2 polynomial. And those roots, again, are where the polynomial is equal to 0. So I put in an x value into some polynomial function, I get 0 as an output. And again, that's the same thing as where it crosses the x-axis. So these roots, we're trying to figure out where it's crossing the x-axis. So the rational root theorem that we're going to work with. This theorem says that integer roots, integers meaning not rational for this piece, so integers like 2, -5, 15, those are integers. We hit right on the number. There's no decimal, there's no fractional amount to them. Integer roots must be plus or minus factors of the constant in P of x. So say I had some polynomial, P of x is 3x³ plus 2x² minus 7x plus 15. Integer roots must be plus minus factors of the constant. What is the constant in that polynomial? Colin, what do you think is the constant in that polynomial? Would it be a multiple of like zero numbers? Nope. So no matter what I put in for x, what stays constant? What do you think, Colin? So say I put x is -5. So this term is going to change. This term is going to change. This is going to change. 15 won't change. That's why it's called a constant. Okay? So this is the constant of the polynomial. The constant's always going to be here at the end when you put it in standard form. That's what it says, plus minus factors of that constant. So for this one, my plus minus factors of 15 are what can I multiply to get 15? Well, I can do 1 and 15. And that plus minus means I'm going to go plus minus 1 and plus minus 15. If I had 1, 15, that works, but if I had -1, -15, that still gets me to 15. But I could also have plus minus 3 and plus minus 5. So this first bullet point, integer roots must be plus minus factors of the constant. So that would be my list of plus minus factors of that constant. Now your rational roots. So this is what everything's going to be working with today. Will be, as a fraction, all of my plus minus factors of the constant term, which is what we just found, divided by plus minus factors of the leading coefficients. So what is, in this polynomial function I created, p of x, what is the leading coefficient? 3. Okay, this is the leading coefficient. And again, it needs to be in standard form, with descending exponent values. Leading coefficient is simply going to be that number in front of your highest exponent. Okay, so what we're going to be focusing on, no matter how complex, how long the polynomial gets, rational root theorem says, all right, we're going to start at the front, and then we're going to work our way to the back. We're not going to do anything in between. Start at the front, jump all the way to the back, and that's it. Okay, this is one that you should star, box in, whatever in your notes. This is what we are going to be working with. This is the rational root theorem. Okay, so let's actually look at finding a rational root. I say list all possible rational roots of this polynomial function. Okay, so I'm going to have a big long list of all possible rational roots. And again, that possible is the key word. It's not guaranteed that they are. It's giving me a starting point. Within this list that I create, I will have possible rational roots. All right, you don't have to write this down. You just wrote this down. Well, we know our rational roots come from plus minus factors of the constant divided by plus minus factors of the leading coefficients. So what are my factors of the constant? Joel, what are the factors of the constant? Yep, plus minus 1, plus minus 5, as far as I can go. All right, and I'm just starting to list these out. Factors of that leading coefficients would be plus minus 1 and plus minus 2. Therefore, all the possible rational roots, I'm going to take my constant divided by leading coefficient. So that would be plus minus 1 all over plus minus 1. So I just write that as plus minus 1. So there's one possible one. And then I'd have plus minus 1 divided by plus minus 2. So I can simply write that as plus minus 1/2. But then I have to do it again. I'm going to do plus minus 5 divided by 1, which would just be plus minus 5. And then plus minus 5 divided by plus minus 2 would be 5/2. So these are all the possible rational roots. This is not, we're gonna have to test it to see if it is an actual rational root, but this is the possible one. This is how I create my list. I simply take one factor of the constant divided by one factor of the leading coefficient, and just continue down the line until I get my list. All right, these ones are pretty easy because there's only 2 factors of each one. If you get more factors, then it becomes a longer list that you're working with. Okay. You do. What are the possible rational roots of this polynomial? So still for practice, I would list out the constant ones and the leading coefficients, and then make sure you divide each to get your list of all of them. And this one will be a longer list. Okay, so we should have started out with finding the constant. So my constant is 2, so plus minus 1 plus minus 2 would be my only factors. The leading coefficients, this one, there's 4, so plus minus 1 plus minus 15 would work, but also plus minus 3 plus minus 5. Now it simply goes through that progression. I'm going to start with the first one, and then I'm going to divide it by every single one there on the bottom. Then go to the second one and divide it by every single one there on the bottom. Okay? You do not need to duplicate possible rational roots. So this first one, we ended up with 1 over 1, and then we had further down the line 2 over 1. If we had had like a 2 over 2, that becomes 1 again. You don't have to write it a second time because you've already accounted for it plus minus 1 at the very beginning. So you don't have to duplicate if there's some that will simplify to be a term that you already have listed for possible rational roots. Okay, and again, these are the possible ones. These are not all going to be roots. This simply gives us a starting point where to work from. Okay. All right, so starting on the handout that I gave you, using the rational roots theorem. So there's a longish process to actually using this rational root theorem in its entirety. So step 1 and step 2, we just practiced on these last 2 slides. So find the constant term factors and the leading coefficient factors. Use that to list out all possible rational roots. So we did step 1 and step 2. Now we're going to expand on this and go to step 3, which is to test each possible rational root in our polynomial until you find a root, meaning your polynomial equals 0. So this is that remainder theorem that we talked about a couple days ago. If we put our 0 into our polynomial, we should get a 0 as an output. So if we get a 0 at 2, we test 2 and it works. That is going to be a 0 of the polynomial. We can use that then to continue to factor using synthetic division. So rational root theorem allows us to factor much more complex polynomials. Once we have it in factored form, then we can determine exactly what the roots are. Because if we end up with, say, x plus 2, x minus 5, and then say we might end up with 3x minus 7. would be in factored form. Well, from this, I could jump and say, well, x would equal a -2. My zeros would be when x is -2, when x is 5, but also when x is a 7/3. So we're trying to get it into this factored form to determine what those actual zeros would be of our larger polynomial that we're starting with. Okay, so into your handouts. So state the possible rational zeros and find all zeros. All right, and you can write on this paper so you don't have to write it in your notebook. Okay, so the polynomial is already there, 15. And so this example, we're going to go over more slides because that's only one problem there on your handout. So state the possible rational zeros. So that's step one, or that's the first part of this question. We're going to do that here in our step 2. But then ultimately, we're going to find all of the zeros. So our factors are a constant, would be plus minus 1, plus minus 2. Factors of our leading coefficient, plus minus 1, plus minus 3, plus minus 5, plus minus 15. Okay, this is an extension of what we've already done. We're continuing this problem. All right, and so we listed out all of those zeros. We just did that on the last slide, but let's write it again. Plus minus 1, plus minus 1/3, plus minus 1/5, plus minus 1/15. But then also plus minus 2/1, plus minus 2/3, plus minus 2/5, and plus minus 2/15. So that was the first question, said state the possible rational zeros. Those are all our rational zeros. Now we're going to continue on. So we have all of these rational zeros listed here. We want to test each possible rational root in our polynomial p of x until you find your polynomial equals 0. So this is literally testing it, like we have to do it. So if I tried p of 1, because I know plus minus 1, 1 is a possible rational root. So if I put this into my polynomial, 15 times 1 cubed minus 32 times 1 squared plus 3 times 1 plus 2. This is that remainder theorem. If I get 0 as an answer, I know that that is a 0, and if it's a 0, I can make it into a factor binomial. Tell you, when you put this in your calculator, work this all out, ends up being -12. All right, so that doesn't help us, but it helps us to identify that this is not a root. So then we have to continue on. Let's try -1. So if I put -1 into my polynomial, so I'm just putting in -1 to every single x value. This one ends up being -48. Okay, that's great, but it doesn't help us. So we have to keep going. Let's try p of 2. So if I put in 2 for all of these, if I put in 2 for all of these, this one does get 0. Ah, that's good. So therefore, I know, so these 3 dots in a triangle means therefore. Therefore, x equaling 2 is a root. Okay, a root or a 0. And if x equals 2 is a root, we know that x minus 2 is a factor of p of x. Okay, so we're kind of working in the reverse direction that we've been going. So if 2 is a root, that means as a binomial, it'd be x minus 2. Again, if I try to make that binomial equal to 0, the only way to do it is if I put 2 in there. Okay, so we are going to use that. So this was step 3. Test each. Once you have one that equals 0, grab onto that. We're going to use that. We couldn't do anything with 1 and -1. All we did was rule out that those are not roots. So we know if we were to graph this polynomial p of x, if we were to graph it, it's going to cross at x equals 2. But we need to keep going. All right, since we know 2 is a root, so this polynomial I can now factor and say, well, it's x minus 2 times something. I need to figure out what that something is. And to figure out what that something is, we use synthetic division. So we put our press box here. What goes up into our press box is 2. So the actual 0, that goes right into our press box. And so we are using synthetic division on our original polynomial. So this is 15, -32, 3, and 2. We're going to bring down the 15. 15 times 2 is 30. And remember, we add with synthetic division. So we get a -2 becomes -4. Add those together, we end up with -1 becomes -2, and we do get 0, which we already know, but this confirms that this works. So we have a remainder of 0, so that's good. That again confirms that 2 is a 0, which is what we want. But now we can rebuild our polynomial. This would be -1 is my constant, -2x, and 15x squared. So that goes right up here. So 15x squared minus 2x minus 1 is the other missing piece of my polynomial after I factored out x minus 2. Okay. So now the last step is to actually determine the roots from the factored form. So this one we already know. We already know this root that x equals 2. But 15x squared minus 2x minus 1, we do not know our roots. We need to factor that. It's a quadratic. We can factor that. Let's do it with our cross. So this would be a -15. That adds up to be a -2. You know, if I have 15 and -2, I could have a -5 and a +3. In order to factor this, this is 4 spot because of the 15x squared. So it'd be 15x squared minus 5x plus 3x minus 1. Do our groupings. Could factor out a 5x. And so this becomes 3x minus 1. Conveniently, this is 3x minus 1, so all I had to factor out was a 1. So I end up with 5x plus 1, 3x minus 1. And then I'm still going to bring down this x minus 2 just to complete it. So fully factored, our polynomial is x minus 2 times 5x plus 1 times 3x minus 1. This tells me that x would be a +2, x would equal a -1/5, and x would be a +1/3. Final answer. I only gave you 2 homework problems for today, okay? Because these take a while. Okay? If you follow the steps, the process this falls into place. Okay, we're not done yet. We're not done yet. Okay. Okay, but if you follow these steps, this is why I gave it to you in a handout, so you could have it all listed out. So don't lose that piece of paper where you have it already written out and you're ready to go. Okay, let's do one real quick that let's do this one. So we'll be faster on this one. Okay, so state all possible rational zeros and find all of the zeros. So this one I want to be specific on. We can kind of combine a few steps together. Well, I don't need to individually list out my constant, my leading coefficient factors. I'm just going to do that right away. Okay, so I know my possible, so this is really step 2. Because this was a 1, that makes it really easy. So I'll write it out here just so we can see. So my constants would be plus minus 1 and plus minus 3. My leading coefficient, LC, is just plus minus 1. So that makes it easy. All I have is plus minus 1 and plus minus 3 because I'm dividing by a plus minus 1. So those are all my possible ones. So now I have to test 1, -1, 3, -3. That's all I have to test. Well, I know the next step is after I get a 0, I'm going to go ahead and put that in to my synthetic division and continue on from there. Okay. For the sake of time, I'll tell you that if you put in 3, or I'm sorry, if you put in -3, you get 0. All right. So -3 is going to go in here for my synthetic division. It's going to be 1x cubed, 3x squared, 1x, and 3. Bring the 1 down, be a -3. That ends up being 0. This becomes 0, 1, -3, 0. There we go. So what we have is our polynomial is going to be equal to x plus 3 times, on this one, it's going to be x squared plus 0x plus 1. Okay, because remember, this is 1, this is 0x, and this would be 1x squared. So 0x you do not have to write, so really it's just x squared plus 1. This one, so I know here that x would be a -3. Here I have x squared equaling a -1. So if I undo the square rooting, x would be a plus minus square root of -1. We can work with that. So this would be plus minus I times the square root of 1, which is just 1. So this would be just a plus minus I. We knew that this was x to the third, so there's 3 solutions. So my 3 solutions are -3 and plus minus I. So we can have imaginary numbers also as solutions. We could have factors that do not have all of the exponents listed out. And so you need to make sure that you are, when you're using your synthetic division, that you're accounting for these zeros. And then when you're undoing your square root, you can still work with imaginary numbers, plus, minus. Don't forget all of that. All right. So that one's quicker. So there is an IXL, and it's talking about listing out passable rational roots. It's not working through the whole problem. So Algebra 2 tab, L10, we're going to go all the way to a 70. But then these 2 additional problems are in Schoology. So it says state the possible rational zeros and find the zeros. So you have 2 problems that you're going to work through, like that big long example that I gave you on that handout. Take it, those problems are listed in Schoology too. But take a picture of that, submit it via Schoology, but then also work on that IXL.